I want to take all of the conic sections, ellipses, parabolas, hyperbolas, all of them, and discuss how to shift their centers. What changes happen to the equations? If we know the equation, how do we determine center? And from the vertices, foci, asymptotes, all the rest of the pieces, the same way we were doing in the previous couple sections. Here is where all of these formulas are combined into one sheet. This is on our candlestick. It's in two different places. It's under the handouts section, both as a PDF and as a Word document. This is the PDF version. It's in the exam review section and will be attached to the final exam. You don't have to memorize this. This will be given to you. But notice all of my equations are now changed to adjust for the changes I'm going to do today. So let's think back about moving equations. We did this back in algebra in chapter 2. We looked at the effect on a graph. So here's a function, x squared. That also happens to be a parabola. There's the graph of y equals x squared. If I want to move that up 3 units, what's the new equation that's 3 units higher than this one? How do I move an equation up 3 units? I just add 3 to the y values, right? So if I want to change the y values to be 3 units higher, I say, oh, I've moved y by adding 3 to it. What if I wanted to go down? I just subtract, yes? What if I want to move left or right? How do I get over to that equation? I'm going to take the equations we have above, where we moved up or down. I'm going to move those changes over to the y side. So instead of writing this equation, y equals x squared plus 3, I'm going to write it y minus 3 equals x squared. Since I changed the y, I'll put the changes with the y. Then the other equation becomes if I move this change, and here's where I noticed something weird. David, you said if I wanted to move it up 3, I added 3. But when I write the equation this way, when I wanted to move it up 3, I subtracted 3 from the y side. And here, if I want to move down 1, I add 1 to the y side. It's kind of backwards, isn't it? I think I have a way around that, but let me run with this for a second. The reason I want to think of it that way is because now I'm going to think about shifting to the right. The right is the positive direction for x. So my brain says I should add 3. But if I add the 3 to the x side, that'll be backwards. So let's subtract 3. Grab your graphing calculators. Let's see if this worked. Graph for me x squared and x minus 3 squared. This one side. And again. So when I graph y equals x squared, I get exactly the picture I'm expecting from an x squared. I get that centered parabola of width 1, focal diameter 2. Sorry, focal diameter is 1. So I get exactly what I'm expecting here. If I then go and I add to that the equation x minus 3 squared, that is shifted to the right by 3. My shifting is backwards. If I wanted to end up over here, what equation do you think I should use here? Well, wait a minute. First of all, I'm only over by 2. So it'll be y equals x plus 2 squared. So my shifting seems to kind of go the wrong way. Here's how I'm going to sort this out. When I think of shifting up or down, it's backwards. Subtracting goes down, adding goes up. Well, let's write the adding as if it was subtracting a negative. Oh, okay. So if it's y minus thing and the thing is positive, we're going up. If it's y minus thing and the thing is negative, we're going down. So I have to remember, I don't ever think about it as adding or subtracting. I always want to think about it as subtracting. Always subtracting. And then the number tells me which direction I'm going. If I'm subtracting 3, I'm going up. If I'm subtracting negative 3, I'm going down. And it'll work the same way for left and right. I just think of it as always being subtracted. And then if h is positive, we go right. And if h is negative, we go left. And that means when I write x plus 2 squared, I'm really thinking of it as x minus negative 2. And that's why this one went left. So here's my shortcut. I can move my equations left, right, up, down by switching out y for y minus a number and switching out x for x minus a number. Hang on a second. We had the equation for a parabola in general, right? We either wrote x squared equals 4py, or we wrote y squared equals 4px. Those were our formulas for the general cases, yes? Not anymore. Now I'm going to write x minus h squared was 4py minus k. And over here, I'm going to write y minus k squared equals 4p x minus h. Now, what change does this make to my parabola? Well, it moves the parabola up or down by k, moves it left or right by h. Let me go back to the pictures we were looking at a minute ago. What that moves is all the points, but it moves the point that was 0, 0. The vertex now gets moved exactly by h and k. So in these two cases, my vertex changes. And once my vertex changes, everything changes relative to that. So this one is still opening up or down. And that depends on the number p. If p is positive, we go up. If p is negative, we go down. How far? We go up by p or down by p. The vertex to the focus and the directrix. So I change the way I get the information out of my problem. I do the same thing over here. This one's going either left or right. It goes to the right when p is positive, it goes to the left when p is negative. How far? Well, from the vertex, we go over to the right or over to the left by p. So if I have the equation, I can build a picture. There's just one problem. Here is an example. Where is the vertex of this parabola? Say again? Almost. Remember, my shifts are backwards. I have to think of it as y minus the number. This number is a positive 4. So we go up 4. Right, because this is x minus negative 2. So the shift there is negative. We went left and up. And remember, these are h and k. That's what those were the letters I was using earlier, h and k, same letters. Does this particular parabola Open up, down, left, or right. How do you know? Well, that's the shift. But if the x is negative, that moved us to the left. But it could move us to the left regardless of which way we open. Yes, we just moved over. Because so that means opens left because that's negative for the p. How do I know it's left, not down? Negative means either left or down. How do I know it's left, not down? I'm not saying you're wrong. I just want you to help me understand it. Aha, whichever one is squared. When the y is squared, we're either left or right. When the x is squared, we're up or down. Since the y is squared, we're left or right. Since the p is negative, we are left. Fabulous. So let me start doing the other pieces. It's the parabola. It's got a focus. It's got a directrix. Focus, directrix. Now, I find it easiest to do this visually, but that's me. So I'm going to make a crappy little picture down here, and I'm going to say, hey, wait a minute. We went 2 units to the left and 4. Here's my vertex V. I am supposed to open to the left. Curve goes around the focus. The focus should be over to the left. It should be over 3 units. The directrix should be 3 units the other way. So, what are the coordinates for the focus? That is correct. -5, 4. I moved 3 units further left from the vertex. Right? Last time we would have just said -3, 0. But what I'm doing is I'm adding that to this. And now the directrix. The directrix is a line. Is this line x equals or y equals? The vertical lines are x equals. What number? 3 units the other way. We got it. And now I can draw a picture. Even if it's a bad picture, I can draw a picture. It's going to go like that. So the shifts change all the rest of the information I have, because I have to adjust all that information to compensate for moving this point from 0, 0 to where it is. I can literally think of picking the whole graph up and shoving it over 2 units, 4 units, like I drew it on glass and just slid it across and up. To that end, these are called rigid transformations. because glass doesn't bend. At least it shouldn't. Questions? My problem is that this was not the equation I was given in the book to start this problem. The textbook actually gave me this equation. And it said, hey, this is a parabola. Tell me all about it. And I went, you've got to be kidding me. How do you know that's a parabola? I'm sorry? My y is squared and my x isn't. Which means I should be able to rearrange this to look like the formula I want. Crap. I got to go all the way back to chapter 2 before we had the quadratic formula. A process called completing the square. Only way for me to figure out what this quadratic looks like is to complete the squares that aren't perfect squares yet. That should be y minus something all squared. But in order to be y minus something squared, it's got to have the right number on the end of it, and this is the wrong number. So when I do completing the square, what I'm doing is I'm rearranging my equation. I'm taking the quadratic expression and I'm making it something plus or something minus squared. So we can either do this in with everything else or we can do it separately off to the side here. I'm going to do it both ways so I show you both of them. Let's take the quadratic expression. Quadratic expression is all the stuff that's just got y's. Let's pull it out. Now, in order for that to be a quadratic that looks like one of these, I need to know what these look like when they're multiplied out. So pick one of these and let's multiply it out. I'm going to take this one. What do you get when you multiply that out? What's that expression when you multiply it out? Y squared minus 2YA. What was the last one? Almost. That's not quite right. Because if I do a minus A times a minus A, I get a plus A squared. I'm going to rearrange this, so I'm going to write it y squared minus 2ay plus a squared. The thing to notice is that the number a is in there and in here, right? The coefficient of the y term is 2a. So that means here, the a is half of that. And that's the number that needs to go on the end here once I square it. So let's take that number and square it. What's half of negative 8? Square that. 16. And that is a perfect square. It is now a complete square form. That's why this process is called completing the square. Back in chapter 1, page 116. To make a perfect square, take half the middle number, square it on, and you fill in the little gap that makes a complete square. This is a geometric idea. The first person who wrote it down in Babylonian 4,500 years ago, and actually drew this picture to show why it worked. So, this is what I should have instead of this. So now I can go back up to that equation, and I can say, oh, I'm going to take that 12x plus y squared minus 8y plus 40, and I'm going to say, really, that's 12x, I want y squared minus 8y plus 16. But if I add 16 to this side, I have to add 16 to the other side. Does that make sense? You can't just arbitrarily put 16 in the middle here. But then this becomes the square. And remember, in my parabolas, in the equations for my parabolas, the square term is alone. So let's put everything else on the other side. And when I move everything else to the other side, what's 16 minus 40? And if I factor the 12 out, I have the formula that I can now use the way we did before. I gave you this, but the book gave me this. I need to do this work to make the equation look like what I want it to look like. I have to do the completing the square to be able to use the properties I know on my formula sheet. My formula sheet only shows me the completed equations. So I have to make it look like that. This is not obvious, but every time I see a square term and then the same variable, I want to have the right number to make it something squared. And if I don't, I have to fix it. Questions? We'll do more. I can go the other way, though. I can give you the information and then ask you for the equation. So here's another problem. If I tell you the vertex is at 1, -1, and my directrix is y equals 3, find the equation for this parabola. Now again, I'm visually driven. So I say to myself, let me draw the picture of what I know. One, -1 would be there. There's my vertex. Where is my directrix? What kind of a line is that? Horizontal line. By the way, this is enough. This is sufficient information. Because from this, you can tell me what the value of P is. What's the value of P? I kept saying that P was the distance from the vertex to the focus, right? But it was also the distance from the vertex to the directrix. So this distance, that's P. How far is that? Except we're going down, right? Because we're supposed to go away from the directrix. So this is really the absolute value of P. Absolute value of P is 4 down. So P is -4. There's my focus, 4 more units down. And that means my parabola is going to go that way. Wait a minute, it's going to go that way. Which is squared, x or y? That is correct. X is squared. If the x is squared, then my equation looks like x minus h squared equals 4p y minus k. I know h, I know k, I know p, I know my equation. Where's h? Where's k? H and k come from my vertex. Go back up here, right, h and k. H goes with x, k goes with y. Same every time. So x minus 1 squared equals 4 times something times y minus -1. There's where my sign changes. I know what P is. P is -4. That goes right there. If you really want to, you could multiply those together and write this as -16, y plus 1. But if all I say is, what's the equation, you could stop right here. That's perfectly acceptable. The vertex is always the same distance to the focus, the same distance to the directrix. It is halfway between the directrix and the focus. As long as I have two of those pieces of information, I can get P. I need either the directrix and the vertex, the directrix and the focus, so I know we're halfway between, or the vertex and the focus. I just need two of the three. Then I get P. Questions? If it works for parabolas, it works for ellipses, it works for hyperbolas. There's just one problem. In the formula for an ellipse and in the formula for hyperbola, both of them are squared. Which means I've got to do my completing the square twice. Food. But let's start with one that's already been completed. Here is an already complete ellipse. How do I know it's an ellipse? Well, Dr. Sassmore, you said so. And you believe me, you fools, you. Look at the form of the equation. It's equal to 1, that's a good thing, that makes an ellipse or a hyperbola. The middle is added. Ellipses are added, hyperbolas are subtracted. Both squares, plus in the middle is an ellipse, minus in the middle is a hyperbola. One square is a parabola. So, I move my ellipse. Wait a minute. The ellipse is based around the position of the center. The center was at 0, 0. So when I shift by h and k, I shift the center of my ellipse, and then everything is built around that. So in this case, the h and the k are not the vertex anymore, they're the center. So in this case, what do I have for a center? Almost. That's a plus, right? And shifts are backwards, so it's 2, -3. Always h and k are always subtracted, so it's x minus h, y minus k. That plus, I got to convert. Great. I went right and down. That means the vertices went right and down. The foci went right and down. The minor axis points went right and down. The whole thing is going to move right and down. How do I get vertices and minor points and foci? Those come from A, B, and C. So what's A in this ellipse? Almost. The 9 is A squared. Because it's always the bigger one. And that makes this one B squared. Hey, since the bigger one is under the X term, that means that it goes horizontally. The long direction is left, right. Major axis is horizontal. We now know that A equals 3. That means my vertices are 3 units to the right, 3 units to the left. Of what? Of my center. That is exactly right. So I take this number and I add or subtract the 3. Three units to the right, 3 units to the left. My minor points. If the major is horizontal, then the minor is vertical. And that comes from B. Now, you can leave this as the square root of 8. You could simplify it to be 2 square root of 2. You could write a decimal, 2.828, whatever the rest of it is. I'm going to leave it as the square root of 8 for the moment. What direction do I go? The square root of 8 units. We said those were the vertices. My vertices were this way. So where are M? This way. Which means I change the Y value of this. So my minor points change the Y value because the minor axis goes up and down. By the way, that's enough to draw me a picture. Because those are where the box is, right? And I fill in the oval inside the box. Two, -3. Vertex at 1, 2, 3, 4, 5, -3, there's a vertex. 1, 0, -1, there's a vertex. I shouldn't have written that number there. I scribbled over my vertex. Minor point is up -3 plus 2.8. That's like -0.2. That's all the way up there for a minor point. And then 1, 2, 2.8 down. There's my other minor point. And that means I can draw in the little box. And my ellipse should look like that. If I want a better drawing, I need to use the thumbtacks and the string, which means I need my foci. Where are my foci? Vertices come from A, minor come from B, foci come from the equation to get C. So I've heard 3 different equations come out of 3 different mouths here. Fortunately, this is on our formula sheet. When we are adding for an ellipse, we're subtracting to find C. It's C squared is A squared minus B squared. Oh, I have those numbers. A squared is 9, B squared is 8, so C squared is 1, which means I go 1 unit. Which way? Side to side, because the foci and the vertices are on the same sides. Foci have to be here and here. Notice those foci are pretty close together. This is a mostly round ellipse as opposed to a stretched ellipse. The eccentricity of this ellipse is 1/3. The closer it is to 0, the more this looks like a circle. David, you had a question?
Is it 1 unit from the V or 1 unit from the center?
It's 1 unit from the center. Everything's based off of where the center is. Whew. So please notice, once the equation looks right, getting the things I want is not difficult. Tedious, but not difficult. The problem is getting the equation to look right. Claim of the morning, that's an ellipse. Sure is. If that's an ellipse, the equation should look like the other equation, right? Boy. Means I need to do my rearranging. I need to do my completing the squares. Once for x and once for y. I find it algebraically convenient. Take the number that's on the end that doesn't have an x or a y on it, throw it on the other side. And to put the x pieces together and the y pieces together. That way I've grouped everything, kind of like we saw in the book on page 116, to do the completing the square. But go back to the previous problem where I did the completing the square, and the number in front of the square was a 1. The number in front of these squares is not a 1. Well, that's not very nice, is it? So I'm going to factor. In both of these, I can pull out a 9. In both of these, I can pull out a 4. Let's fill in what got left behind. What x goes here? If I pulled out that 9, what should be here? 2x. What should be here if I pulled that out? And now I can do the completing the square just like I did before. I take half the middle number. What's half the middle number? Square that. Add that here. I take half the middle number. What's half the middle number? Square that. Add that here. But if I put it on the left, I have to put it on the right. So over here, there needs to be a +1, and over here, there needs to be a +4. But wait, there's more. Stuff on the left is inside parentheses. It means the stuff on the right needs to be inside parentheses also. And it needs to have the same number in front of it as it does on the other side. Because when I put that 1 in there, I'm really multiplying it by the 9. So when I put the 1 over on the other side, I have to multiply it by the 9. When I put the 4 in here, it's really multiplied by this 4. So when I put the 4 in here, it's really multiplied by this 4. Okay, that's actually helpful to me. What's this stuff over here? Multiply that out, add all that together. This is now a square. It's x, 1, a plus. This is now a square. It's y, 2, and a plus. Because that's x squared and a squared, so that must be a. And the plus brought down. If this is an ellipse, what's the number supposed to be all the way over there on the right? 1. So let's divide everything by 36. Oh, catch me. Those are squares. They should be squared. That looks right. But I have a 9 on top and a 4 on top. Let's get rid of those. What's 36 divided by 9? If I cancel the 9, I get x plus 1 squared over 4. And here, if I cancel the 4, I get y plus 2 squared over 9. That's an ellipse. That's exactly what I wanted to see. Where's the center of this ellipse? That's exactly right. Because they're h and k, and we got to do them on the inside. They're backwards. I got to make it subtraction. Does this one go up, down, or does it go left, right? The bigger numbers under y, it goes up, down. That means that a squared is 9, and b squared is 4. Well, wait a minute, what's c squared? C squared is a squared minus b squared. That's 5. You can now tell me, where are the vertices? Where are the minor axis points? Where are the foci? You have all the numbers. All you have to do is adjust your center. If I want the vertices, I need to go up or down. That's what you told me, by A. So the vertices go up or down by A. The minor points go left or right by B. And the foci, on the same way as the vertex, go up or down by C. It worked. It ain't short. But the best part about this is that almost all of this is algebra, not trig. This is okay. I've done this crap before. This is all right. Questions? I started this problem by saying this was an ellipse. And therefore I knew what equation to look towards. How do I know that this is an ellipse? Just looking at the equation. What about in general? For example, this equation. Parabola, ellipse, hyperbola. It's one of them. All right. It turns out there is a general way to tell. Well, if the x and y are squared, that means it's not a parabola. It could be an ellipse, it could be a hyperbola. How do I know which one it is?
Because the x squared is negative.
One of them is negative, one of them is positive. That should be subtraction in my squares, right? And if my squares are subtracted, that's going to be a hyperbola. Let's go back and look at the last equation. The last equation was an ellipse. And yes, indeed, both of those numbers were positive. As a matter of fact, the numbers on the squares are all I need. Here's a shortcut formula. A general conic section. Now, you'll notice there's no B. B comes later. I will explain B later on. There's a term missing from this. The reason that I'm doing that is because these conic sections are all parallel to the x-axis or parallel to the y-axis. They're either straight up, straight down, straight left, straight right. They don't get to be tilted or twisted. And when I add the other term with the B in it, they get twisted. We're going to leave that alone for the moment. If AC equals 0, then this is a parabola. Think about that. The only way for the product of two numbers to be 0 is for one of them to be 0. And that means I either have no x squared, I only have the y squared, or I have no y squared, I only have the x squared, I only have one square. That's a parabola. Oh, you sneaky booger. If the product of those two numbers is positive, then they're either both positive or both negative. If they're both negative, multiply everything by -1, and then they're both positive. If the product of the quadratic coefficients, the a and the c, is positive, we have an ellipse. And Dominic, you're exactly right, because if we multiply those two numbers, we get something negative. -1 times 4, then this is a hyperbola. And now I know what equation I should be looking to get. That's where having those equations in front of me tells me what I need to know. So I know this equation is a hyperbola, which means I should be able to make it look like the normal equation for a hyperbola. Let's do that. So I do the same thing we did last time. I throw the number all alone to the other side. I put the x bits together. I put the y bits together. And we go to town. But just like with the last one, the number in front of the x squared is not a 1. The number in front of the y squared is not a 1. I need to factor the number out. Now, in front of x squared, it's just minus sign. So that's a negative 1. But in front of the y, it's a 4. Sorry, the y squared. So when I factor that out, I get something different. What completes my two squares? The square on the left in the x's and the square on the right. Sorry, the left-hand square, the right-hand square, because they're both on the left side of the equation. The x term, what's the constant in there to complete that square? Say again, David? That's a 1. And this one? Half the middle term is negative 2. Negative 2 squared is 4. So now over on the other side, in the parentheses, minus 1 times 1. In the parentheses, plus 4 times 4. So here on the left, I have minus parentheses x plus 1 squared plus 4 parentheses y minus 2 squared. And on the right, negative 11 minus 1 plus 16, I have a 4. But this should be a hyperbola, which means it should be equal to what on the right-hand side? 1. Divide everything by 4. Now, I'm going to do one more thing just to make me personally happy. I'm going to switch the order so that the subtraction is in the middle. And that means I write this y minus 2 squared over 1 minus x plus 1 squared over 4. That, strictly speaking, isn't necessary. But now I know what's a, what's b. Well, I know what's a squared, I know what's b squared. I know where the center is because I know h and k. Does this hyperbola go left, right, or up, down? Why do you know it goes left, right?
Well, I was thinking of an ellipse, but it's because the 4, like.
Right, because you think the 4 is bigger.
Yeah, that's what I was thinking.
In an ellipse, you would be correct, but in a hyperbola, it's always the direction of
It's going to go up, down, because the y is positive.
the positive fraction. And that means that this is a squared, because a is always the one that goes with the positive. That makes this b squared. HK, where's my center? Oh, I caught you. No, you were right with 2 and -1, but the -1 is with the x. It's always x with h and y with k, regardless of what order it's in. So the 2 and the -1 were right, but it is -1 for x and 2. Aha, because it's always x and h, y and k. Wonderful. So, vertices. Which direction do I go to get vertices? I go up and down because that's our opening direction. How far? 1. The minor points. Well, if vertices were up and down, then minor is left and right, which means I'm changing x. That's this one. Before I go any further, I'm going to draw the box. -1, 2, there's my center. Okay, the vertices are up and down by 1. The minors are left and right by 2. So my box, I hate my pencil. My box looks like this. We're going up and down, right? This is going to be a wide hyperbola. That's okay. For a hyperbola, there are 2 more things I need. I need the foci. Where are the foci? I need a formula for C. What's the formula for C in this case? Because there's subtraction in the equation for C is addition. Oh, so C squared is 1 plus 4, that's 5. So C is the square root of 5. And that's up or down. So that's 2 plus or minus the square root of 5. Now the square root of 5 is 2 1/4. So 1, 2, and a little bit more. 1, 2, and a little bit more. The other thing I need are the asymptotes. Now, I'm going to draw them. So out comes my ruler, and I go corner to corner in the box. Both ways. There are my asymptotes. What is the slope of this line? The asymptote going from lower left to upper right. How do you know? Wait a second. Right 2 up 1 means the slope is rise over run. And this slope? Negative. Same run, but a negative rise. Please notice, the number under the y is 1. That's A. The number under x, B, is the square root of 4. These are A over B. If it was going this way, they'd be B over A. This is why I just say it's y number over x number. So these are lines, right? We just came up with slopes. What's the equation of a line? Well, I don't want to use mx plus b because this isn't going through 0, 0. The point that I know is on the line is the center. So I have a slope and a point. Y minus y value equals slope x minus x value. Y minus y value equals slope x minus x value. When we did them on Tuesday, we just wrote y equals mx, but that was because we were going through the point 0, 0. This time we're going through the center. And now I can draw my picture. I would like to point out to you one other thing. Remember, this is a programmable computer. And that's where all the programs are. But even if we didn't program something, just like my phone, there's an apps button. It's all in here. There's the parabola equations. And it even shows me left, right versus up, down. Here are the hyperbola equations. It even shows me left, right versus up, down based on which one. Son of a. But if I want to use this to do this one that we just did, that's this form, I need to feed it the numbers. So I say H was -1. Oh, sorry, A. A was 1. B was 2. H was -1. K was 2. Graph. All in here. Okay, so there are 2 questions remaining, and one of those is, what am I supposed to do with that B? And what are the other ways I can do some of this stuff? And that is next time. Please note that next class, you have 2 sections of work due. The ellipses and the hyperbolas. We'll see you all then.